Hello students, now we shall see the next part of this photochemistry. So already seen what happens by the the starting part of photochemistry we have seen, that is interaction of electromagnetic radiation, that is with matter. So I have already sent some video regarding this. So you will see numerous splitting of this light from cosmic rays, infrared rays, all those rays. So now we shall see what is this electronic excitation, or it has some types of excitations. How many types of excitations are there? So before that we should know one part. There are when you come to this photochemistry, so it is reaction which happens by the absorption of light. This one you should be remember very carefully, and H mu always plays a very important role in this photochemistry. So whenever in other chemical reactions, when you go into the inorganic or organic or any other reactions, there may be some catalyst which plays a role to the reaction or speed up of the reaction. H mu, that is light, plays very important role in this photochemical reaction. So here it is very clearly given. Photochemistry is study of reaction that are brought about by the action of visible or UV light, that is ultraviolet light, when a molecule absorbs electromagnetic radiation. So this radiation is usually, whenever I say electromagnetic radiation, it is usually in a visible or ultraviolet region. It gets excited. When a molecule absorbs electromagnetic radiation, it gets excited. The amount of energy that such a radiation contains depends on upon its wavelength, that is E is equal to H mu is equal to Hc by lambda. So H mu plays very important role in further coming reactions, photochemical reactions. When the absorption of light brings about a chemical reaction, it is referred as photochemical reaction. So most organic molecules have even number of electrons, with all electrons paired, which state is called as singlet state. So this is also a very important point to be noted. So we'll come across singlet state, triplet state. So ground state of any molecule is called as singlet state. So reactions are brought about by absorption of light, and these are called photochemical reactions. So organic molecules, they have even number of electrons in theirs, and these electrons are paired up in their ground state, and this ground state we call it here, especially in photochemistry, as singlet state. So when electromagnetic radiation is absorbed in the visible or UV region, the molecule excited to the higher electronic state. This involves promotion of electron from bonding molecular orbital to the anti-bonding molecular orbital. So these type of excitations are depends upon to which from which bonding molecular orbital to the which anti-bonding or non-bonding orbital. So these electrons gets excited. On this basis, now we have some different types of electronic excitations. The absorption of light energy of molecules in the visible and ultraviolet region involves promotion of electron from the bonding orbital. So here bonding orbitals are only two, that is sigma or pi, to the corresponding anti-bonding orbital, sigma star or pi star. So bonding two orbitals, anti-bonding two orbitals. Bonding orbitals are sigma or pi, anti-bonding orbitals are sigma star or pi star. The non-bonding electrons are generally not involved in the bond formation. So on this basis, that is whenever a chemical reaction occurs by absorption of light, electrons get excited from the ground state to the excited state from bonding orbitals such as sigma or pi to the sigma star or pi star. So there are also chances from electrons which are not participating in the bond formation, that is non-bonding electrons. These also get excited. So on this basis, there are four types of excitation found in most of organic molecules, which are as follows. So one is sigma to the sigma star. Alkanes contain only sigma bonds. they do not have pi or n electrons, that is non-bonding electrons, in their molecules. Hence they can be excited by sigma to sigma star. So here you can clearly understand the excitation of electrons from sigma to sigma star happens in case of alkenes, since they do not have any pi or n electrons. So second type of excitation is N to sigma star. Oxygen and nitrogen atoms of alcohols, amines, ethers, etc. contain unused long pair of electrons, that is N. So these are not participating in any type of bond formation, hence they can be excited by N to sigma star, that is non-bonding to the anti-bonding. Third type of excitation is pi 2. This is pi star, please correct, that is not pi to sigma star, it is pi to pi star. Compounds of alkenes, ketones, aldehydes, esters, etc. having unsaturated pi bonds consist of pi electrons, hence they can be excited by pi to pi star excitation. That means in compounds, that is our molecules, like alkenes, ketones, aldehydes and esters, excitation of electrons can happen from pi bonding orbital to the pi star antibonding orbital. This is the third type of excitation. So fourth type of excitation is N to pi star. Aldehydes, ketones, esters, etc. have pi electrons as well as unused lone pair of n electrons, that is non-bonding electrons. They can also undergo N to pi star excitation as well as above 3 promotion, that is above 3 sigma to sigma star, N to sigma star, pi to pi star also can happen in the case of these aldehydes, ketones, esters, etc. So below is the clear schematic representation for different types of electronic excitations. So first below it is the energy level, it is given. On the left side, complete left side is given sigma, pi, n. Above these are bonding orbitals, that is n is non-bonding orbital, sigma and pi being the bonding orbital. Pi star, above the pi star is sigma star. So these two are anti-bonding orbitals. So after this we can see sigma to sigma star, that is first type of excitation. Second, n to sigma star can happen, and n to pi star can happen, and pi to pi star. So these are different types of electronic excitations which can happen in these organic molecules by absorption of uh, light in the visible and ultraviolet region. So order of energy required for various electronic excitation is sigma to sigma star is having requires more energy. So greater than that requires non-bonding to sigma star antibonding, pi to pi star and n to pi star. So I think you have understood these are different types of electronic excitation which can happen in the organic molecules. So please remember, sigma to sigma star is possible, n to sigma star is possible, yeah, pi to pi star is possible, n to pi star is possible. So there is no sigma to pi star or pi to sigma star. So these are not possible electronic excitations, and these electronic excitations are not at all possible in any of the organic molecules when we study this photochemistry or photochemical reaction. So then what is this fate of photoexcited molecules? So now we shall see what is the singlet and triplet state. Fate means, so what happens to the electrons which are present in the ground state as well as the excited state. Here when you, so we are generally speaking, when you come to chemistry in organic or organic chemistry, we generally speak of ground state as well as excited state. So only we are aware of these two states, but when you come to the photochemistry, we need to understand what is the singlet state and triplet state and why these are called so. So there are, as we know, even number of, that means each subshell or each orbital, that is Each subshell can have a pair of electrons. So S subshell or S orbital can have pair of two lone pair of electrons, and P subshell has again split into three orbitals px, py, pz. Each px can maximum accommodate two electrons, py can accommodate pair of electrons, and the spin of these electrons are always opposite in direction. So this we are aware of these type of electrons present in the any molecule. And when we come to the organic molecule, there are even number of electrons in a typical organic molecule, and these electrons are usually paired in ground state, and this ground state we represent as S0, that is a singlet state. So when the electrons present in this singlet state, so now instead of ground state we go on speaking as singlet state. Absorption of light of correct energy if it occurs without spin inversion, and so electron spins remains paired in the excited state, the state is commonly called excited singlet state. So excited singlet state, if it is the first excitation you can call it as S1, if it is second excitation you can call it as S2, so depending upon the excitation. So without inversion of spin of the electrons, if the electrons get excited or jump from the ground state, that is SO singlet state, to the higher state without spin inversion, then we call it as only as excited singlet state. It may be S1, S2 or S3 or so on. However, in many cases electronic excitations followed by spin inversion, thus giving rise to a new excited state with two unpaired electrons occurs, then this state is called an excited triplet state. So this state is called as an excited triplet state. So if excitation occurs with the inversion, spin inversion, and giving rise to a new excited state with two unpaired electrons. So now paired electrons get separated and becomes unpaired electrons. So this state is called as an excited triplet state. Now we call it as T1. So direct excitation of ground state or triplet state is not possible, and hence T1 is populated via S1. So that means the electrons cannot get excited directly to the triplet state. So from S0 to T1 is not possible. These electrons can go from S0 ground state to the S1 excited singlet state or S2 excited singlet state 2, and from there they can come to the T1 or T triplet state. So from S0 to T is not possible. S0 to S1 T1, S0 to S2, S2 to T1, or S2 to S1 and S1 to T1 is possible. So this is explained in the Jablonski diagram. So in the note it is clearly given singlet state do not split in a magnetic field, while triplet states have three possible energy states in an applied magnetic field. A triplet state is more stable than corresponding excited singlet state. So fate of excited molecule can be explained clearly by the Jablonski diagram, which is a pictorial illustration of different energy states which are absorbed by a molecule. So when the molecule absorbs UV radiations, it gets excited and promotes to the excited singlet electronic states S1 or S2 or S3. In the above state, molecule collides with the neighboring molecules, and after 10 to the power of minus 13 to 10 to the minus 11 second, it comes back rapidly to the S1 state and releases energy to the environment. This entire process is called as energy cascade. In the figure 36.2, you can clearly see. So below is a ground state for an organic molecule, that is S0. So first S1 is first excited singlet state, S2 is an excited singlet state 2, and right side, so what it is T is given is it is a triplet state. So according to this Jablonski diagram, if an electron of an organic molecule, if an organic molecule absorbs UV radiation, a light from the UV radiation. That is, if it absorbs UV light radiations, the electron which is present in the ground state, that is singlet state S0, can go to the S2. So as first arrow mark gives the clear representation, S0 to the S2, that is excited singlet state. From S2, if it comes back to the S1, then here you can see it can come to the S1. So lifetime of singlet state is relatively long, hence this state can be undergo different physical and chemical processes. A molecule returns to its ground state from its excited singlet state S1 or S2 by giving up its energy as heat. So this process is called as internal conversion, that is IC. It is represented as IC. So here it moves from S0 to the S2. From S2, the electron comes to the S1. It cannot come directly to the S0. If it goes to the S2, it has to come to the S1. During this process, that is internal conversion, it may lose energy in the form of heat. So arrow mark, so it is given from S2 to S1. From S1, if the molecule returns to its ground state from excited singlet state S1 or S2 by emitting energy in the form of light radiation within 10 to the power of minus 9 seconds, then the process is known as fluorescence. So from S2 or S1, if it returns to the S0, then it is also called as internal conversion. Here, if it happens within 10 to the power of minus 9 seconds, then this process is called as fluorescence, and energy is lost as an fluorescent light. So it is given as HVF, that is energy lost in the form of fluorescent light. So this process is generally slow and not very common. Smaller molecules and rigid molecules are example of this process. The emitted fluorescent light is of slightly lower energy than absorbed light, hence has longer wavelength. And most molecules in S1 state can undergo an InterSystem Crossing, that is ISC, InterSystem Crossing, to the lowest triplet state. The first excited triplet state T1 is more stable because it has lower energy than the first excited singlet state. Hence, InterSystem Crossing process is an energically downhill process. So if electron which has exited from S0 to S2 and it comes from S2 to S1, it is an internal conversion. From S1 to S0, if it comes, then it is also called as an internal conversion, and energy is here lost in the form of a fluorescent light. Instead of that process going from S1 to S0, if it comes via a T state, from S1 to T, then this T is a triplet state. So then this process is called as InterSystem Crossing. That is, most molecules in S1 state can undergo an InterSystem Crossing to the lowest triplet state T1. The first excited triplet state is more stable because it has lower energy than the first excited singlet state. Hence, InterSystem Crossing, that is ISC process, is an energically downhill process. After some time, the triplet state also drops to the ground state S0 by emitting a photon of light by the process, and this process is called as Phosphorusine. So if an electron which has gone to the S2 comes to the S1, it is an internal conversion. From S1 to T, then it is intersystem crossing. From T, it comes to the S0. This is also an intersystem crossing. And if it by electron goes to the S0 through or via T, that is triplet state, by loss of some energy by emitting a photon, then this process is called as Phosphorusine. As the triplet state is more stable because it is lower to the first excited singlet state, it is more stable than a singlet state. Hence, triplet state can undergo chemical reaction more rapidly than singlet state, and therefore photochemistry is largely the chemistry of triplet state. So right here you can see many variety of processes happening in the one single organic molecule by the excitation of electrons from a ground state to the excited state by absorption of UV radiation. S0 is a singlet ground state, S1 and S2 are excited singlet state, T is triplet state, IC is internal conversion, ISC is intersystem crossing, HVA, that is energy is absorbed. HV, as we know, an amount of energy, that is a photon of light, it is absorbed. HVF, energy lost as fluorescent light, HVP, energy lost as phosphorescent light. So here some physical processes occur by the excited molecules or S0 plus by absorption of an UV radiation of light. It is electromagnetic radiation. If it goes to the S1, it is excitation single state. S1 to the S1 plus heat, then it is vibrational cascade. That is if it loses heat, energy in the form of heat. S1 to the S0, if it comes electrons, comes back to the ground state from S1 to S0 by emission of that is loss of some energy, then it is called fluorescence. From S1 to T, that is S1 to S0, if it again if heat is lost, energy is lost in the form of heat, then it is internal conversion. If it comes from S1 to T, then it is intersystem crossing. T to T, by again loss of heat, then it is vibrational cascade. T to S0, by loss of heat, then it is intersystem crossing. T to S0, it is singlet ground state. By emission of photon, then it's called Phosphorusine. So we have observed one is energy cascade, so another one is fluorescence and Phosphorusine. So we can see many processes occurs in a single organic molecule by excitation of electrons from singlet state to the ground, that is ground singlet state to the excited singlet state, and coming back to the singlet ground state via a triplet state. So right, this is the explanation for fate of excited molecules, or you can say a Jablonski diagram. So then what is this quantum yield? So quantum yield, it is represented by a symbol called phi. It is called as phi. The efficiency of photochemical reaction is expressed in the terms of quantum efficiency or quantum yield, which is expressed by symbol phi. It is defined as number of molecules reacting per quantum of light absorbed. So phi is given by number of molecules reacting given time by number of quantum of radiation absorbed in the same time. The energy absorbed per molecule of the reacting substance is called 1 Einstein. Now phi becomes number of mole reacting or produced by number of Einstein absorbed. So instead of number of quantum of radiation absorbed, now becomes number of Einstein absorbed. So value of phi is rarely a unit in actual practice. Unity in actuality, its value varies from 10 to the minus 2 to 10 to the power of 4. If psi is greater than 1, it indicates a chain reaction, whereas if psi is less than 1, shows either a non-chain process or a reversible process. So quantum yield is measured generally by a process called actinometry. So this is about the types of excitations, Jablonski diagram, that is fate of excited molecule, and also quantum yield.